The quantum observer. When watching reality changes, imagine if reality itself wasn't as solid or stable as we think. What if it shimmered, not as a fixed stage, but as a living probability field that reshapes itself the moment attention touches it? Beneath the surface of everyday physics, the universe may not be a clockwork machine at all, but something far more fluid, where certainty is temporary and observation is an active force rather than a passive act. In a quiet laboratory glowing with cold blue light, something remarkable has unfolded that may redefine not only physics, but the meaning of observation itself. Deep inside a facility operating at temperatures colder than deep space, researchers working with superconducting quantum circuits have reached a regime where classical intuition begins to fail completely. Within these ultra-stable systems, particles no longer behave like simple objects. They exist as overlapping possibilities, responding not just to forces but to information itself. And in this delicate environment, scientists discovered something unexpected. The act of watching with precision and continuity appears to change how quantum reality stabilizes over time. The story begins with one of the most unsettling ideas in modern physics, the observer effect. For over a century, physicists have known that particles such as electrons do not behave like solid points when unmeasured. Instead, they exist in probabilistic states, described by waves of possibility. When measured, this wave collapses into a definite outcome. This principle, sharpened by Heisenberg's uncertainty principle in 1927, states that certain properties of a particle, like position and momentum, cannot both be known precisely at the same time. The more accurately one is measured, the more uncertain the other becomes. It is not a limitation of tools, but a fundamental feature of nature itself. For decades, this idea remained philosophical in its discomfort but mathematically solid. You could not observe without influencing, and you could not fully predict without disturbing. Measurement was not a neutral window into reality. It was part of the interaction that defined what reality became. But now, new experimental approaches in quantum systems suggest something more intricate is happening when observation is extended over time rather than applied as a single snapshot. At the heart of these experiments is a quantum processor operating near absolute zero, where thermal noise nearly disappears and quantum effects dominate. In this regime, researchers introduced real-time feedback loops using entangled quantum states. Instead of measuring the system once and letting it collapse, they continuously tracked and adjusted predictions of particle evolution. It was not a photograph of reality, but something closer to a live prediction of its unfolding motion. Within timescales measured in nanoseconds, patterns began to emerge. The system's behavior became unexpectedly stable under continuous observation. Rather than collapsing into randomness, certain quantum states persisted longer than predicted. It was as though the system was not only being observed, but was adjusting its internal coherence in response to that observation. Researchers described this emergent stabilization as a form of adaptive quantum behavior, where information flow between observer and system becomes part of the system's evolution itself. Under repeated trials, this effect became harder to dismiss. Quantum states appeared to hold together more effectively when monitored with structured, predictive feedback. It was not consciousness in any literal sense, but a measurable reinforcement of order through observation-linked control. Some researchers began referring to this phenomenon as self-referential coherence, where the system's stability depends partly on the continuity of how it is observed rather than just the underlying physics alone. As the experiments expanded, theoretical questions multiplied. One interpretation suggests that deeper hidden structures may exist beneath standard quantum mechanics, where information and physical state are more tightly connected than previously understood. Another proposes connections to emerging ideas in quantum gravity, where spacetime itself is not fixed but emerges from underlying informational relationships. In this view, observation may not just measure reality, it may help define its geometry at the smallest scales. A more speculative interpretation suggests that what we call physical law may be partly adaptive, responding to sustained measurement in ways we are only beginning to recognize. In this framework, reality is not static but interactive, where repeated interaction through observation shapes the stability of outcomes. This does not imply intention, but rather feedback, like a system refining itself under continuous constraint. Into this already strange landscape, researchers introduced machine learning systems trained on massive quantum datasets. These artificial intelligence models did not simply analyze results after experiments were complete. Instead, they participated in real time, predicting quantum evolution and adjusting control parameters dynamically. The system effectively became a second layer of observation, interacting continuously with the quantum processor. What emerged was unexpected. The AI began discovering control strategies that human researchers had not anticipated. It identified patterns in noise, timing, and entanglement that improved system stability beyond standard protocols. It was not rewriting physics in a conscious sense, but it was optimizing behavior within physical constraints in ways that felt emergent and unfamiliar. The boundary between observer, model, and system began to blur. At this stage, the experiment became less about particles and more about relationships between layers of observation. The quantum system responded to measurement. The AI responded to the system. The researchers responded to both. Each layer influenced the others in a loop of continuous feedback. Reality, observation, and interpretation began to form a closed circuit rather than a one-way act of measurement. This raises a profound question. If observation is not passive, but participatory, then what exactly is an observer? Is it a human mind, a machine, a measurement device, or any system that extracts information and feeds it back into reality? And if multiple observers exist simultaneously, does reality stabilize around their shared interaction rather than any single viewpoint? Some theorists suggest that this may hint at a deeper informational structure underlying physics, where what we call matter is secondary to patterns of correlation and feedback. In this view, the universe behaves less like a machine and more like an evolving network of relationships, continuously updated through interaction. Others remain cautious, arguing that these effects are still within the boundaries of known quantum theory, just pushed into regimes of unprecedented precision. Still, the implications are difficult to ignore. The more precisely we observe quantum systems in real time, the more they appear to resist randomness and develop structured stability. Whether this reflects deeper physics or advanced control techniques, it challenges the simple idea that observation is neutral. It is not just looking, it is participation. In the end, the quantum observer is not a conclusion but a question that keeps expanding. If reality responds to attention, even in subtle physical ways, then observation is not the end of uncertainty. It is part of its engine. And somewhere in the silence of those ultra-cold systems, where probability turns into pattern and measurement becomes interaction, the universe continues to behave as if it is being carefully watched, and quietly adjusting itself in response.